and they have two sensors, and they assumed with some theoretical argument, they assumed this functional form between the growth and the pressure drop as a quadratic dependence, and then using that boundary conditions and these pictures of the snapshots of the real experiment, they solved the Laplacian equations for these 2 points, what should be the pressure drop at 2 points and 2 sensors, and they compared that with the experimental result from the sensor. So, and it shows that it matches nicely, but it's not a conclusive picture. Okay. So, the second author of this work, they contacted us, and we have discussions whether we can do it, measure it directly from the simulations. So, now before presenting the result, I go through the quickly one slide for the model. So, it's we call dynamic pore network modeling, where the pore space is discretized with networks of pores with simplified geometry, and each pore has this Washburn equation, just generalization of Darcy equation. So, Q as a Q varies with delta P minus Pc, here Pc is the capillary pressure due to all the interfaces, and this is the summation of all the pressures, and it behaves like this. H2 gamma is a Young Laplace and plus the shape of the tube, and then it's an incompressible fluid. So, the sum of all the flow rates are 0, and then you get a set of linear equations, you solve it, and to time step with time and advance the interfaces. And there is also snap up and coalescence of these things are there. And then we can do this for the steady state simulation, which I already showed the result before, in two different ways, by open boundary conditions, the same as the experiment is done, or in the periodic boundary condition. Here you can see that here is the viscous fingers, and here is the stable displacement type of. And then we can do it for the drainage simulations also. And these are capillary fingerings in this regime, and you can see this growth is governed by the local disorder in the capillary forces, and then this is a viscous fingering, and also this is also the model can also generate the stable displacement when you push inject a high viscous fluid into a low viscous fluid. And these are the results. So, what do we measure? We measured the growth and shape as a function of the distance from the tip, because if you see all the growth and everything is depends what is the position from the tip also. So, we generate a dynamic coordinate system which is fixed on the tip, and everything is measured from that. And if you think about the averaging over time and different samples, then this statistical profile is basically statistically invariant with time if we measure with this coordinate system. And these are the many simulations we done as a function of capillary number and viscosity ratios, and you see things goes from the capillary fingering towards viscous fingering regime. And this is a comparison of the shape of the submantellar. So, this is for our simulation, and you can see that they are different from the DLA and also from the submantellar, and there is a continuous variation of the lambda as a function of the capillary number. It's not a constant number. And then the last part, the growth versus pressure drop. So, if you think about the growth, phi is a growth, and there is a distribution of the capillary thresholds in the pores. So, the growth of the fingers will depend on how many fingers are invaded, and the pressure drop across. This is from the same Washburn equation. And if we consider a simple functional form of this uniform distribution, we can work it analytically, and we can end up with two different regimes. For one regime we can have the quadratic dependence, and another regime we have linear dependence. But we don't in our real system we don't have this in uniform distribution. It's a complicated relationship between the all pore properties. So, we go to the simulation, and we find the growth, which is the rate of increase of volume divided by time, and then if we integrate over the x-axis, we get as a function of the z, because it is symmetrical on the x-axis. And this looks like this. So, growth mostly happens close to the fingers, and then it dies out. And then local pressure drop we can find out from the pressures in individual nodes, and this is the non-wetting pressure. You can see there is not much variation because it is a low viscous fluid. This is the wetting pressure, and this is the difference between these two. You can see that wetting pressures, the pressure drop is high in the close to the fingertip, and then it's almost horizontal. and that's why it is almost no growth here. So this is the threshold pressure, because even if the pressure is non-zero here, you don't see any growth. So from this horizontal value, we can find out the threshold pressure. So we measure the threshold pressures. This is the last slide, and for many simulations, and this looks like this for two different viscosity ratios, and you can see that they don't depend on the viscosity ratio, because this is a function of the surface tension, not the viscosities. And then we compared, so now we have the pressure drop, we have threshold pressure, and we can measure, we have the growth, we can measure the beta, and they looks like this. So these are the power laws, and clearly you can see the similar as the steady state flows. Here also you can see the same non-linear regime and the linear regime, crossover to the linear regime, which generally people already know from a long year, but this is new. And this looks like how the experiments looks like. So there's non-linear regime close to between 2.5 to 3, and then it crosses over to uniform, crosses over to the linear directions. And these were just published 2 days back, 5th of March, first day of the conference. So it's properly fits here, I think. Okay, so that's all. This is a quick summary. So we studied the viscous fingers, and then which shows in the nonlinear growth interpreted capillary numbers, and then crosses over to the Laplacian growth at high capillary numbers, and also the shapes can be different from the Chapman-Taylor fingers or from DLA. And some open questions. The first question appears that if we know the beta from the steady state, whether it will be the same for these two, for the same system, because the originally seems to be the same the distribution in the disorder of in the capillary thresholds, and also how to relate this exponent for different functional form of this disorder. Yeah, so that's all. Thank you very much.
Thank you, Shantanu. Any questions? I had one question. In the beginning, you showed there were 2 regimes. With capillary pressure,
I mean this,
and the pressure gradient. Right, these 2. So is there any, I mean, the transition seems to be very abrupt. I mean, there is no, are the mechanisms very, what is the difference? Why do we see this 2 regimes?
Yeah, I mean, what in the simple form, what we believe that here the new paths, because there's a threshold pressure is there. So when the threshold pressures is not all, the global pressure drop is such that not all the pores have crossed its threshold pressures. New paths are appearing in the system. So when you increase the pressure drop, the flow rate in individual conducting paths is higher, increases, and also the number of paths are also increases. So the flow rate increases much faster than the pressure drop. And what here we think that almost all the possible paths are already there. So it's only increasing the flow rates in the existing possible paths. So,
but the transition seems to be very abrupt.
Yes, I mean, it's a log scale. There may be some variation, but yeah.
Okay. Are there any other questions? If not, then I think we will go for a coffee break and come back here by 3. Okay. Oh, sorry. Yeah, media center.